So here's a circuit diagram for an LC circuit. That's the oscillator circuit. That's the one in which when you first put it in position A, then the capacitor charges up to some maximum value. There's an electric field in the plates between the capacitor, and then you throw the switch into position B, and that electric field starts to disappear as current is conducted through the inductor, making a little bit of magnetic field appear. And this process continues. By the time the current has reached its maximum value, the electric field is down to 0 in the plates of the capacitor, and the magnetic field reaches its maximum value. Now you might think at that point, if the electric field has gone to 0, there's no longer any charge, and that's true, but the process doesn't stop. At that point, the magnetic field has a maximum value, and it can't suddenly just shrink to 0 without inducing a current. So as the magnetic field starts to shrink to 0, the induced current causes it to continue to flow in a clockwise direction, and the capacitor gets charged in the reverse fashion. And next thing you know, the magnetic field has all disappeared, and the electric field returns to the capacitor, but in the opposite direction. So not only is magnetic field and electric field oscillating, but so is charge on the plates and the current in the circuit and the energies in both of the devices. In fact, everything is oscillating in this circuit. The charge oscillates according to the equation Q equals Q maximum times cosine of omega t, where Q maximum is equal to the product of the capacitance and the battery voltage, and omega, the angular frequency of oscillation, is equal to the square root of 1 over LC. As you know, this is akin to a mass attached to a spring, oscillating about its equilibrium position along a frictionless x-axis. You pull the block back and establish some amplitude, and that's like putting this switch into position A and establishing some initial amount of charge. And then moving the switch to position B is like releasing this mass and letting it to begin to oscillate. Overshoots the equilibrium position. For a moment, the spring is fully compressed, and the vibrations continue back and forth indefinitely. Now, what if we were to add something that has to push through the air, like a big flag or a sail or something like that, to the massive object, and we pull it back and we release it from rest? Now it encounters some air resistance as the air pushes against this sail, and that causes a type of oscillation known as damped motion or damped vibrations. In the LC circuit, if we were to graph the way the charge on the capacitor plates varies with time, you know we just get a graph of something that looks like a cosine curve, where positive Q and negative Q represent the bounds for the charge, and this cyclic behavior just goes on and on and on. And that's the same graph as you would have for position as a function of time for the basic mechanical oscillator. But as soon as you introduce some force of air resistance, then you get a graph of position versus time that shows the oscillations are sinusoidal but exponentially decaying. So the bounds don't remain the same, the bounds are decaying exponentially, and that's what a graph of damped harmonic motion looks like. Now, you might recall that this is a big throwback here. There's an equation that describes position as a function of time. For the case with no damping, it's really simple. The position is just equal to A cosine omega t. But as soon as you have damping, Then the equation says position is equal to A times E to the negative B over 2mt times cosine of omega prime, instead of omega, omega prime times t, where omega prime is not the square root of k over m as it is for the case without damping. Omega prime is equal to the square root of k over m minus b squared over 4m squared. So with the correct value of b, if I can create the right drag coefficient for this sail, I can establish something known as critical damping, where the oscillations go to zero frequency. And that would be the case if b squared over 4m squared were equal to k over m. We can cancel out one of those m's. We can say b squared would have to equal 4mk, or the critical drag coefficient for critical damping would be 2 times the square root of mk. Well, I don't know if that sounds familiar or not, but that's the behavior of this circuit, or at least analogous to the behavior of this circuit. This time, if we throw the switch into position A, we'll still get an initial charge equal to CE, but now when we throw the switch into position B, the energy isn't just going to be transferred from the electric field to the magnetic field without any waste of energy. Current would have to flow through this resistor, and energy would be dissipated away as wasted thermal energy or transferred to the environment as heat. So if we express Kirchhoffs loop rule, we'd get an equation that says, well, let's start from here. And initially there's the negative and there's the positive terminal. And let's see, if we apply Kirchhoffs loop rule, start from here and work our way back around, then we just have to add the voltage on the capacitor, the voltage across the resistor, and the voltage across the inductor. So let's see, from negative to positive, that's going to give us Q over C. Okay, and then, when current flows in the same direction that we're tracing our way around the loop, then there's a loss of voltage, right? This is the high potential side of the resistor. That's the low potential side, so we get minus R times I. And then, as long as this current hasn't reached its maximum value yet, that means current is still increasing. There's a value of di dt, so the induced voltage is a back EMF across the inductor. So there's the positive terminal, there's the negative terminal. So again, applying Kirchhoffs loop rule, tracing our way around, this would be minus L di dt, and now we're back to where we started, so we can say that equals 0. Let me express this in a slightly different way. We get Q minus RC, and then instead of, you can see I'm just multiplying both sides of the equation by C, right? And instead of writing I, I'm going to call it dq dt. Okay, then we get minus LC times, now I'm not going to call it di dt, I'm going to call it the second derivative of charge with respect to time, and that's all equal to 0. Let's think about this. What we're saying is there's a function for charge. Charge is a function of time. It's going to vary, but whatever mathematical expression describes the way in which charge varies with time, there should be some direct relationship between that function and its first derivative, and there should also be some kind of direct relationship between that function and its second derivative. So functions that have a direct relationship between their own expression and the first derivative are exponentials. In fact, here it's a negative constant multiplied by the first derivative. So what type of function can I take the first derivative of and get a negative constant times that very function. So if we guess Q equals Q maximum times e to the negative some constant times t, then the first derivative of that equation would give us negative constant Q e to the negative ct. So it's a negative constant multiplied by that original function itself. Okay, so we would expect that the solution to this differential equation probably has something to do with exponential decay. But it would also be a decent guess to think it has something to do with sinusoidal behavior. We could guess that Q equals Q maximum times cosine omega t, and so the second derivative of that equation with respect to time would give us negative omega squared Q cosine omega t, and we recognize all of that is just the expression for Q that we guessed. So here we're getting a equation that describes the way charge varies in time, that when we take the second derivative, we get a negative constant times that original function itself. And that satisfies this portion of our differential equation. So that's not exactly the right guess, and that's not exactly the right guess, but the guess somehow should incorporate both an exponential decay term and a sinusoidal term. So without going through it, I believe it's a little bit beyond the mathematical scope of this class to solve this differential equation. If you've already taken a course in differential equations, you might be able to verify the solution I'll present to you. An equation that satisfies this differential equation is one of this form. The charge on the capacitor is equal to some maximum value of charge times e to the negative r over 2l times t, also times cosine omega prime times t. Now, let's talk about this value omega prime. For the LC circuit, the one that has no resistance, then we can say it has an angular frequency, or I'll change my terminology, I'll call it omega naught. Okay, so that's the frequency of the circuit without any resistance. The frequency is the square root of 1 over LC. When resistance is added to the circuit, the frequency is the square root of 1 over LC minus R squared over 4 L squared. And by the way, if you compare that expression to the expression for angular frequency for a damped mechanical oscillator, you see there's a very strong correlation between the two. They are both analogous equations to one another. In fact, we should expect some form of critical damping. There's a way in which we can make the frequency approach zero. At that point, we can say that moving the switch into position B would cause the capacitor to discharge in such a way that there is no oscillation. It would discharge through the inductor, and just at the point that it becomes fully discharged, the current has faded to zero by that point. That would be a case of, something like critical damping. We would have added a critical value of resistance to the circuit. So let's try to come up with an expression for the critical resistance value in an LRC circuit. Let's move this out of the way. We'll get to this example problem in a moment. So the only way omega prime could equal 0 is if 1 over LC is equal to R squared over 4 times L squared. Let's cancel out one of the L's, cross multiply, and R squared would have to equal 4 times L over C. So R critical would have to equal 2 times the square root of L over C. Okay. Here's an example problem. Part A, what's the critical value of resistance that would make for zero angular frequency in this circuit? Well, that's the equation we just derived. The critical value of resistance is equal to 2 times the square root of L over C. So if we plug in the example values, this is 2 times the square root of 2 times 10 to the negative third Henry divided by 15 times 10 to the negative 12th farads. Grab your calculators and see what you get. So I get a critical value of resistance of about 23.1 kiloohms. Well, here's part B of our example problem. We're told that the resistance is less than that. The resistance is less than the critical value that creates for critical damping. In fact, the resistance is 10 kiloohms as opposed to 23.1 kiloohms. So the question is, what frequency of oscillation would you get for this circuit? The frequency is the square root of 1 over LC minus R squared over 4L squared. So here we get a value that can be found if we grab our calculators and plug in the given information. The inductance is 2 times 10 to the negative third henries. The capacitance is 15 picofarads. The resistance is 10 kiloohms. That's 1 times 10 to the 4th ohms. We have to square that term. Divided by 4 times, and the inductance is 2 millihenries, and that also gets squared. Okay, so let's take this term by term. So we have omega prime is equal to the square root of 3.3 repeating times 10 to the 13th minus, now the other term gives us 6.25 times 10 to the 12th. So let's find the difference between those. And we get the square root of 2.71 times 10 to the 13th. So omega prime is equal to about 5.2 times 10 to the 6th. And the units have to be radians per second. Well, it's hard to relate to frequencies expressed in radians per second. I'm much more familiar with frequencies measured in hertz, or cycles per second. For every cycle, there's 2 pi radians. 2 pi radians is equal to 1 cycle. So I can find an expression for the traditional frequency as opposed to the angular frequency. The standard frequency is the angular frequency divided by 2 pi. So if we take 5.2 times 10 to the 6th radians per second and divide it by 2 pi radians per cycle, then we get about 8.28 times 10 to the 5th cycles per second, otherwise known as 828 kilohertz, which is somewhere within the AM radio frequency range. Okay, so just an example problem on the LRC circuit.